started. Okay. So today's topic is to discuss about the transfer function, then frequency response, uh, some Bode plots, etc. So, so I'm starting with the transfer function. So transfer function basically why we need transfer function. Okay, we talk about gain of the amplifier. So gain of the amplifier is how bigger the output signal will be when compared with the input signal. If I'm talking about the gain of the amplifier, if the output and the input both are numeric, right? Like if I say the voltage gain is 10, and if I give an input voltage of 2 millivolt, then definitely with a gain of 10, I'm going to get 20 millivolt. Similarly, if the input is 1 volt, then the gain is 10, then I'm getting a 10 volt. So basically, it's very easy to calculate the input and output voltage or a gain. Means there are three quantities. If any two quantities are known, then third quantity can easily be found out. But what would happen if the input is not a simple numeric number? Like the gain is not a simple number 10. It is in the form of a differential equation, right? Your function is in the form of a differential equation. Then it becomes very difficult to calculate the gain or the output or the input, any of the three quantities, if any one of them is in a differential equation form. For that particular problem, we need to convert that differential equation into a algebraic equation. Okay, so that is being done with the help of a Laplace transform. So there are fixed formulas which we go through after some time, and you can use those formulas to convert your differential equation form into a simple algebraic form. Okay, so when is the S domain? S domain means your Laplace transform. If the function is represented by capital F in brackets S, so that immediately you should know this is a Laplace transform function. So it is usual to use a capital letter F for the Laplace transform and a lowercase letter small f for the time varying function. Okay, so this is the difference between a Laplace and the simple time varying function. Okay. So transfer function is what? It is a Laplace transform of output upon Laplace transform of input. The things, the formula is going to remain same. The only thing is that we have converted the differential equation into algebraic equation by following a Laplace transform. So accordingly, the quantities that you are seeing over here have been changed. These quantities that you are seeing. Okay. So earlier they were simple x of t, y of t, and now they are x of s and y of s. Means these are the Laplace functions. The important thing to be noted over here in Laplace, we consider all initial conditions to be 0. Okay, so that is a beneficial for us because we don't want to make our problem complicated. So we assume 0 output when 0 input and 0 rate of change of output with a time when 0 rate of change of input is there. So if you want to calculate anything like excess, you can take this y on the left side, and so this is a simple rearrangement of the things. Okay, and this is your simple gain formula. You are feeding some input to the gain and you're getting some output in the form of xt. Here the things would remain same. Only thing is that you have converted this differential. This is a differential equation. You have converted this into a Laplace transform, and this is being fed into the transfer function, and you're getting again the output in the form of a Laplace transform function. So if you want to calculate it in terms of say time function, you have to take an inverse of the Laplace transform. We'll discuss that as well in the next article. So first of all, there are few formulas that I am telling you. Like first is to obtain the Laplace transform of a differential equation, we have some fixed formulas, okay, which includes quantities that are functions of time. We can use tables coupled with a few basic rules. Like you can see over your screen, unit impulse at 0 time. This one, unit impulse at 0 time has a transform of 1. So unit impulse that has been given over here has a transform of 1. So you need to remember this. Similarly, unit step means this one, this direct input. Unit step at 0 time has a transform of 1 by s, right? We'll be using that in our coming articles. Similarly, if we have a unit ramp input at 0 time, then the transform function would be 1 by s square. Similarly, we will be discussing in the next unit about the input as a sine wave. In that case, your Laplace form will be omega by s square by omega square if you have a sine wave. Similarly, if you have a cosine wave, then your transform would be s by s square plus omega square. These are the basic ones. Okay. So following in the same line, if a function of time is multiplied by a constant, right? You can see there is a function of time. Please switch off your mind. If you have a function of in terms of time, it is multiplied by a, then similarly your transform function will also be multiplied by that constant. So it would be a times fs. Okay. So example you can easily understand. Then I go to the next. If an equation includes a summation, then your transfer function would also be a summation of two functions. Now this is important. The Laplace transform of a first derivative of a function is this one. Okay, dy dt of ft. This is equal to conversion of a. If you have got any function in the derivative form, then this can simply be written as s times fs minus f0. F0 doesn't have any meaning over here because I already told you that the Laplace transform, the initial conditions are 0. So it is simply, if there is a differentiation, which is simply written as s of fs. Similarly, if you have a second derivative, which you can see over here, right, then this would be s square fs square fs minus f0 and d f0. Again, these two are does not have any meaning over here. Okay, so you are left with the s square fs. So you have got the double differentiation, and similarly you have got a single differentiation functions. Then simply for a single differentiation, it will be s times fs. For second derivative, it will be s square fs. Similarly, now you can have a formula for integration. If the function is in the integral form, then this can simply be written as 1 by s times fs. So all these have been summarized over here. Okay, ft is converted into fs, differentiation is converted to sfs, second derivative is converted to s square fs, and integral of ft is converted into fs by s. Okay. Now, after getting your output, right, what you want to do, you want to, because your output is in the form of Laplace transform, so definitely you want it to convert into some meaningful form, and that is in the terms of time. So you have to take an inverse of the Laplace transform. So if you have a Laplace transform in this form, then its inverse would be e raised to the minus at. If it is in the form of this, then this is a function of time. Similarly, you have these formulas. So these are the inverse formula. You should remember that. So those will be helpful for you to solve first order, second order systems or any numerical problem. Now, in the previous lecture, we have considered this first order system, right? So this first order system has all the things, like it has a time varying function, it has a constant function, then it is equal to some kind of a input is being given to the system. So we have all the things, right? Where a0, a1, b0 are constants, y is the input and x is the output. So both being function of time, the Laplace transform of this, because these are the function of time x and y, so we need to convert that into Laplace transform. So already by using the previous formulas on the previous page that I have discussed, differentiation is written as s times the function. X is simply written as x of s, because this x is x of t, this is x of s. And again, capital letter you already remember, we denote the Laplace function. So b naught y times s. Okay. So we can write the transfer function of gs as. So you can have x s common out of this, then ys is over here, then you can take x in the denominator, you can find the gain. Okay, so gain is xs by ys. Xs is your output, ys is your input. So what you get? This is your gain in terms of Laplace function. Okay. This can be rearranged. Now there are some few terms that you can introduce over here, like b naught by a naught. So b naught by a naught is what? We can term it as a g, as a steady state condition. Okay, then a naught a1 by a naught is some time constant. We can replace it as tau s plus 1. So these are some of the replacements you can have in your function. So this is the final function for a first order system. Okay, you must remember. Now, first order system with step input, like we have done in the previous class, we have discussed about the step input and the given to the first order. Similarly, we'll be discussing that over here as well. So when our first order system is subjected to a unit input, then ys would be 1 by s. Do you remember from the previous graph? Should I go back and tell you? So this is a unit step input. What was the transfer function? It was 1 by s. So similarly, we are using it. So we have a unit step input, then our transfer function would be 1 by s. So in the previous class, I told you simply what you do, you multiply your step input with the input given to the system. So by multiplying that, what you are getting, this is the previous function, g by tau s plus 1, you have got from here. You just multiply this by 1 by s. So by rearranging, you can write it in another form as well. So we have got our output as in the form of this. So this is by comparing, this is equal to a by s into s plus a. So from the previous discussion, we know that the inverse of this is equal to nothing but this value. So now we have converted back our output in the form of a function of t. This is a first order system with step in. Now there are few examples have been given. You can one or two examples under this. Like this one, you can take this as a mechanical system. So a thermocouple is there which has a transfer function linking its voltage output V and a temperature input of this. So this is a function is already been given to you. Now what is being asked? Determine the response of the system when subject to a step input of size 100 degrees centigrade. Okay. So what will be your output? It is the gain into the input, as I did in the previous page. So step size input is how much? It is 100 C. So if I'm taking its Laplace, it would be 100 by s. So this was the function gain, and what I did, I multiply this by 100 by s. So this is my output. Okay. Now comparing this with this and taking its inverse form, this is my final output. Okay. So this is how you can calculate. Now it is being asked about to calculate this when time goes to infinity. So you can put that value over here and you can get your final value. This is kind of a very good question on the Laplace transform for a first order system. Similarly, two more examples are given over here. Please attempt these examples. Next, we have a second order system. So while we are taking a second order system, you must remember from the previous class, this was the second order system. Okay, this is your inertia. This is what this was the dashboard system, right? This is what this is the spring system, and this is your force which is applied from external agency. So already you know that when there is a second derivative of x, it has to be written in terms of s square. Single derivative is written in terms of s, and x of t is written as x of capital X of s. Similarly, y of t is written as capital Y of s. Okay. So further taking x's common on the left hand side and rearranging the things, this is the gain that you get. X's on ys is equal to this. Now, in the previous class, we also have discussed about using a damping factor zeta. So by converting that, this was the equation that was discussed in the previous class. So using this again, you can have your gain in terms of a transfer function xs upon ys So this comes out. This is the transfer function for a second order system. Okay. Right. Then what do? You give a step input to the second order system. So step input is what? 1 by s. So then the output transform will be what? The gain into the step input. So you just multiplied the previous gain with the 1 by s. This is what you get. So this can be rearranged again with some modifications. This can be s plus p1 plus making, because this is a quadratic equation. So quadratic equation has two roots. So p1, p2 are the two roots of the equation. So s square plus 2 zeta omega n plus omega, you can solve it further to get the values of the roots. So by solving this quadratic equation, you get these roots, and finally you get the values for p1 and p2. Okay. So now in the previous class, I told you in case of this different mechanical vibration system, we have three kind of a system. When zeta is greater than 1, it is overdamped. When zeta is 1, it is a critically damped. When zeta is less than 1, it is underdamped. So because zeta is involved in this equation, again we'll be solving our transfer function for the three different cases. That is for overdamped system, underdamped system, and the critically damped system. The first thing first case that has been discussed over here, when zeta is greater than 1. So what would happen? The square root term is real because zeta is greater than 1. So you will get some positive number out of this square root. So it is a real number and system is what? To find the inverse transform, we can either use partial fractions to break the expression down into number of simple fraction, or use the. So these are some of the appendix of this book. You can see over there how to solve this particular equation. Similarly, for a critical system, you know that roots are equal to minus omega n when critically damped system, as in the previous class. Similarly, for the under damped system, though some equation it becomes complicated, so this will be your final function. Don't get too much complicated about these things. If you find it to be difficult, let it be like this, and you just prepare up to a second order step input for the overdamped system. Just to try to remember if it's possible. Otherwise, it's not that dated at all. Now you can have few examples of over here, like what will be the state of damping of a system having the following transfer function and subject to a unit step input. This is a transfer function given to you, and this is a step input. So what you will do, output will be just multiplication of these two. So you write it like this, then you solve this quadratic equation, p1 p2 two roots comes out to be -4, as both the roots are real and the same, and so the system is critically damped. Okay, because roots comes out to be same, and for a critical damped system the roots are same, so you can easily judge that the second order system is a critically damped system. Similarly, you can do these one or two. Okay. Next article in your syllabus is if a system consists of a number of subsystems in a series as in figure, then the transfer function of the system is given by. Now series, like you get some final output and ys is the initial input, and this in between this final and initial, say there are like three systems who are working in a series, then by following a chain rule, what you can do, you can replace that x1 by y into x2 by x1 into x by x2. It can easily be say that x2 cancels out with x2, x1 cancels out with x1, but you get xs by ys. Sorry. So the total gain for the system is nothing but a multiplication of individual gains of the system. So when the system is in series, you will be calculating the gains individually for all the systems, and then you will be multiplying them to get the final output of the whole system. Now there's a very simple example over here, like we get three systems, already gains have been given to you, 10, 2 by s and 4 by s plus 3. You need to find out the total gain. What you did is you just multiply all these three and you get the final gain for the system. Now in the next article, what you have is systems with feedback loops. So you can see this figure 2.5 over here. This is the gain, like kind of amplifier or something. This is the output signal which is being fed to the this corrective feedback signal, and this is giving it as a negative feedback. You can see that it's going to the negative. So whatever input is there, whatever output of this system, that is going to be subtracted from the initial. Please switch off your mic, please. So whatever the input is given over here, that input, this output of this feedback is subtracted from this input, and you will generate an error signal which is fed to the amplifier, and you will get the final output, right? So this is kind of a negative feedback you have. So how the gain is working now? Axis is the output. Okay, what is your input? Input is, this is what you have fed over here, minus your negative feedback, HS into XS, because these two are working in a series. So what you have done, you have multiplied both the things and subtracted from the initial input. This is how you are getting your gain. Okay, so this can be rearranged like this, and hence the overall total function can be. Then we have a small example over this. Some two systems are given. You can follow that formula. You can calculate the transfer function. This is negative feedback. These articles are not in your syllabus. So moving to the next unit. Next is your frequency response. Frequency input, you can say. Right. So till now we have considered either a zero input or a constant input or a step input, means a constant input. But now in this chapter we will be considering that the input is also a sinusoidal. That means it is in the form of either of a sine wave curve or it is in the form of a cos wave curve. Okay. Right. So again, if I'm starting with a first order system, then this is the equation, parent equation that I will be using. Only difference is that here the input will be y is equal to sine omega t, right? So what will be the output? The output again have to be a sine, because if the right hand side is a sine wave, then input will also be a sine wave. Well, we must end up with sinusoidal b naught sine omega t when we add a1 dx by dt and a naught x. So this is the same discussion that has been done over here. The cosine is a sinusoidal being just sine omega t, means if I'm adding a sine, then if my output is coming out to be in the form of a cos, again it's a sinusoidal, and again we can represent cos in terms of sine by just adding 90 degree to this. So this applies no matter how many times we carry out the differentiation. Thus we should expect the steady state response x will also be a sinusoidal. Okay. All right. Then we have a phasor. Phasor is what? Phasor is nothing but it's a vector form which has a quantity as well as a magnitude. You must have studied the phasors in your 10+2 class while learning those electrical systems. So here we will be having a quantity as well as a magnitude. This is a vector. So this is how the phasor is named over here. So once it's a vector form, if this is my my final output, then it has two vectors over here, real and imaginary. Imaginary is iota x. Iota is simply written by j over here, small j into x. So my total function would be x plus iota y. Okay. So a complex quantity can be represented by x plus iota y, where x is the real part and your y is the imaginary part of the complexity. So on a graph with the imaginary component as the y-axis and the real part as the x-axis, so that represents a complexity. Okay. So if we take the line joining the point and we try to find out the phase angle for the phasor, so this comes out to be y upon x. And what would be the length of the phasor? This is important. Okay. So length of the phasor would be nothing but under root of x square plus y square, that by simply following the Pythagoras. You must remember that this is how we calculate the length of the phasor, because why I'm saying this is important, while I will be discussing that first order and second order system with you. So in that time, we'll be trying to find out the angle as well as the length of the phasor. So since x is equal to v cos phi, y is equal to v sin phi, that can easily be understood like in this triangle phi. This is your cos function, this is your sine function, this is how this is written over here. And what is total phasor? It's x plus iota y. So this is replacing that cos plus sine. So this is how your phasor has been represented. Okay. Consider a phasor of length 1 at a phase angle at 0 degree. Phasor of length 1 phase angle at 0 degree. So that means we are talking about this. Okay. It will be having a complex number of 1 plus iota 0. Okay. Now consider the same length phasor but with a phase angle of 90 degree. It will have a complex number of 0 plus iota into y. So that means what is the difference between the two? The previous, this one, and this one. The only increment is in the form of a iota. So by just adding an iota, what is happening? You are moving your phasor through an angle of 90 degree. So whenever you are moving or giving a rotation of a phasor anti-clockwise by 90 degree, that is nothing but corresponds to a multiplication of the phasor by iota. Okay? If we now rotate this phasor by further 90 degree, what would happen? We again have to multiply this by a iota. So previously one iota was there, now you have multiplied this with another iota. What you are getting is iota square. But the phasor is just the original phasor in the opposite direction, iota, because first you rotated it through 90 degree, again you have rotated it through 90 degree. So the total rotation is nothing but 180 degree. So that means the direction has completely changed. It is in the opposite direction. So that means we need to multiply it by -1. So what is the value of iota square? It is -1. So that means our supposition of multiplying our phasor with iota for every 90 degree anti-clockwise rotation is perfectly fitting over here. So if we are going to multiply again, means rotating our phasor again through 90 degree, means total angle is 270 degree. That is nothing but 3 multiply of 90, means 3 times multiply of 90 degree. So that means we need to have 3 iotas multiply with each other. So what you are getting is minus. Right. To illustrate the above, consider why I'm discussing this whole thing, because this is the backbone of the further articles. Once you understood this, the other articles are nothing but just follow these principles. Now, to illustrate the above, consider a voltage V which varies sinusoidally with the time according to the equation this. So you got some system 10 sine omega t plus 30 degree. When represented by a phasor, what are its length, its angle relative to the reference axis, its real and imaginary parts when represented by a complex number. So this is kind of an example that you can remember. The phasor will have a length scale to represent the amplitude of the sinusoid. So this is going to be what? 10 volt, simple. The angle of the phasor relative to the reference angle is equal to the phase angle, which is 30 degree over here. So you can read it out from here. The real part is given by 10 cos 30. Okay, already told you in the that x is equal to in the form of cos and y is in the form of sine. So total length of the vector, which is 10 into cos 30, is equal to your x part, and similarly your y will be equal to 10 sine 30, which is 5p. So the phasor is specified by x plus iota into y. So this is how you have found your phasor, right? So this is representing this behavior of the system into a phasor solution. Okay. Now one more is the phasor equations. Consider a phasor as representing the unit amplitude sinusoidal of x is equal to sine omega t. This one. Now differentiating of this, dx by dt is omega cos omega t. Time remaining is only like 3-4 minutes. So let me complete this phasor equation at least. Consider a phase as representing the unit sinusoidal of x is equal to sine omega t. Differentiating of the sinusoidal gives dx by dt as omega cos omega t. But we can also write dx by dt as omega sine omega t plus 90 degree. Differentiation is going to give you cos, and cos can be written as sine omega t plus 90 degree. In other words, differentiation just result in a phasor with a length increased by a factor of omega. Okay, so you have got the multiplication, which is also rotated through 90 degrees. So you got two things. Once you got the x system, you are taking its differentiation. So what differentiation is doing, it is multiplying the phasor with omega and also rotating it through an angle of 90 degrees. So if I'm writing it in the complex notation, so that means we have to multiply the initial with iota omega, because what iota does, it rotates the phasor through an angle of 90 degree. What omega does, it already has been found out from the differentiation that our phasor needs to be multiplied by omega. So by just simply multiplying it by iota omega, we are getting is what? We are getting the differentiation. Alright? So x is equal to sine omega t, we did the differentiation, we got this equation, and from there we just compare it with the complex number. So we have simply found out by simply multiplying our initial phasor through iota omega, we are doing nothing but we are doing the differentiation of the system. So if I am writing this differential equation for the first order system, which is a1 dx by dt plus a naught x is equal to b naught y, what is this differentiation is doing over here? This is just being represented as iota into omega. A1 into x is Laplace, a naught x is equal to b naught y. This is how you have written the phasor equation for the initial first order system. Right? I hope this is understood by everyone. Now this can be rearranged everything, and you can find x upon y. X upon y means you have found this. So if I'm writing it in S domain, this is b naught by s. You can compare this. So s is nothing but over here, it is s is equal to j times omega. Okay. So if we replace s by j omega, we have the same equation. It turns out that we can also do this to convert the s domain to a frequency domain. I think you have understood that in earlier systems, when the input was not sinusoidal. So now if the input is sinusoidal, what we have found out the value of s. S is equal to iota into omega. So if we multiply the system by iota omega, earlier we were using it as a s. Now we are using it as a iota omega if the input is a frequency domain. Okay. So output phasor or input phasor, this is gs is 1 by s plus 1. Got it? So this is simply converted into iota omega plus 1. Okay. So I'm completing my lecture over here. All right. If you have any problem, you can send me a personal